Hello everyone, in this video we're going to review apcalculus BC topic convergence of series. Alright, before we're going to dive into question, let's review some concept behind this topic. So here's the table of the 8 series tests that will be tested on the apcalculus BC exam. The first one is the n-term test. Another name of the n-term test is divergence test. The formula is going to be series A sub n. This test cannot be applied to determine convergence. Alright. Now the series A sub n diverges when limit of A sub n when n approaches infinity not equal to 0 or does not exist. Note that if the series A sub n converges, then the limit A sub n when n approaches infinity equals 0. If the limit of A sub n when n approaches infinity equals 0, the n-term test is inconclusive, right? So which means we don't have the converse of this guy. Now, the next one is the geometric series. You have two different ways to write the geometric series right here. Remember, if k starts from 1, and then this guy must be k minus 1. If k starts from 0, this guy must be k. So you need to be aware of this guy. Alright, the series converges to s sub infinity equals the first term over 1 minus r if absolute value of r less than 1. Alright, this guy is the same thing as this guy, so keep that in mind. Now, the series diverges if absolute value of r greater than or equal to 1. So this guy is the same thing as this guy, right? Which is you learn from algebra 2. Now, P series is going to be given by this formula. Now, this series converges if the power right here greater than 1. Diverges if p greater than 0 less than or equal to 1. Note that if b equals 1, this is called harmonic series, and harmonic series is the special case of the p series. Alright, and the harmonic series always diverges, so keep that in mind. Now, next one, we're going to talk about the intro test. The formula is given by this guy, and we're going to let A sub n equals f of s. Alright. The series converges if the interval from 1 to infinity of fs ds converges. The series diverges if the interval from 1 to infinity of fs ds diverges. Remember that the function fs must be positive, continuous, and decreasing on this interval. Now, next one, the ratio test. The formula is given by this guy. The series converges if limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity less than 1, and diverges if this guy greater than 1. Now, if limit of this guy when n approaches infinity equals 1, then the ratio test fails, right? Now, next one, direct comparison test. The formula is given by this guy. Suppose we have the series that bigger than this series, right? So it could be right here. Alright. So if the bigger converges, the smaller converges, right? So if b sub n converges, a sub n converges. Now, to determine if the series diverges, we're going to compare this guy with the other one. That is smaller than a sub n, right? So if the smaller diverges, the bigger diverges. So if this one diverges, this guy diverges, right? Now, we're going to move on to limit comparison test. The formula is given by this one, right? Now, suppose you have two positive series, a sub n and b sub n. if the limit of a sub n over b sub n when n approaches infinity equals a number greater than 0. Now, the series right here converges if the bottom converges. The series right here diverges if the bottom diverges. Alright, so keep that in mind. If the number L right here equals 0 and the series on the bottom converges, so is the top converges. If number L equals infinity, then the bottom diverges, so is the top. Now, number 3, both series must have positive terms. Now, next one, alternating series test. So, here's 3 different formulas of the alternating series you're gonna see on the AP exam. It could be power of n, it could be n minus 1, it could be n plus 1. Now, if limit of a sub n right here equals 0 when n approaches infinity, and the sequence a sub n right here is decreasing, it means a sub n greater than or equal to a sub n plus 1. Then the series converges. Now, this test cannot be applied to determine the divergence. Now, note that to verify if the sequence is decreasing, you need to show that a sub n plus 1 minus a sub n less than or equal to 0. Or you can use this one right here, a sub n plus 1 over a sub n less than or equal to 1. Or f prime of n less than or equal to 0. So, this guy right here and this guy right here are most popular ways to do it. Now, the last one we're going to talk about is the absolute and conditional convergence. We have 3 possible behaviors of the series a sub n. When analyzing the convergence or divergence of a series a sub n, there are 3 possible cases. The first one, the series converges absolutely. So if the series absolute value of a sub n converges, then the series a sub n also converges. Second, converges conditionally. If the series absolute value of a sub n diverges, but the series a sub n converges, then the series a sub n is there to converge conditionally. Number 3, diverges. If both absolute value of a sub n and a sub n diverge, then a sub n diverges. Now, suppose you given the infinite series a sub n, right? So what you need to do is to find the limit of a sub n when n approaches infinity, right? You have 2 possible cases. Now, you're going to check to see if this limit equals 0 or not, right? If the limit of this series not equal to 0, right? So, you have this case right here. Then, the series divergent by the n-term test or divergent test right here. Right? Now, if the limit of a sub n when n approaches infinity equals 0, so it could be yes. You're going to check to see if the series is geometric. Now, if the series is geometric, then you're going to check the absolute value of common ratio to see if it's less than 1, right? If it's yes, and then the series converges, right? If it's no, and then the series diverges, right? If this series is not geometric, then you're going to check to see if there are positive terms. If no, and then you're going to check to see if the sign alternates. If yes, and then you're going to check to see if the series decreasing. If the series is decreasing, then the series converges. If the series not decreasing, and then you're gonna try absolute convergence. Now after you check the sign and you don't see the sign alternating, and then you're gonna try absolute convergence. If there are positive terms, we're gonna think about the P series first, right? Now you're gonna check to see if this series is a P series. If it is, and then check to see if P greater than 1. If yes, and then the series converges, right? If no, and then the series diverges, right? Now, what if the series right here is not a P series? Think about the integral test. Now, if this one is, the series converges. If you cannot use the integral test, think about the ratio test. If you succeed, and then the series converges. If you cannot use the ratio test, think about the root test. If you succeed, and then the series converges. If not, think about the direct comparison test. If you succeed, and then the series converges. If not, think about the limit comparison test. If you succeed, and then the series converges. Now remember that the upper bound and lower bound of the series is given by integral form 1 to infinitive of f of s ds less than equal to the series a sub n when n goes from 1 to infinitive less than equal to a sub 1 plus the integral from 1 to infinitive of f of s ds. Now, 3 Maclaurin series you need to memorize for the AP calculus BC exam. Alright, the first one, e to the s is going to be 1 plus s over 1 factorial plus s squared over 2 factorial plus s cubed over 3 factorial plus etc. plus s to the n over n factorial. It's actually sum of s to the n over n factorial when n goes from 0 to infinity. So basically you just check the general terms right here, you put it over here, that's it, right? And you know that the interval of convergence of this series is negative infinity to positive infinity. Now the second one is the sine function. It's going to be s minus s cubed over 3 factorial plus s to the 5th over 5 factorial minus s to the 7 over 7 factorial plus etc. plus negative 1 power n times s to the 2n plus 1 over 2n plus 1 factorial. It's actually the series negative 1 raised to the n s raised to the 2n plus 1 over 2n plus 1 factorial when n goes from 0 to infinity. And the interval of convergence of this series is negative infinity to positive infinity. Now here's the trick to memorize the sine and cosine. Remember, sine is the odd function, so you will see the odd number right here, right? Now cosine is an even function, so you're going to see the even number. Cosine s equals 1 minus s over 2 factorial plus s to the 4 over 4 factorial minus s to the 6 over 6 factorial plus etc. plus negative 1 raised to the n times s raised to the 2n over 2n factorial plus etc. It's actually the sum of negative 1 raised to the n s raised to the 2n over 2n factorial when n goes from 0 to infinity. The interval of convergence of the series is negative infinity to positive infinitive. Last one, the geometric power series that appear mostly on the IP exam, which is 1 over 1 minus s. Excavate 1 plus s squared plus s cubed plus etc. plus s to the n. And it's gonna be sum of s to the n when n goes from 0 to infinity. And you know that the interval of convergence of the series is negative 1 to 1. Now let's move on to question 1. What is the interval of convergence of the power series right here? Alright, so the best way for you to do MCQ is to eliminate the wrong answer immediately. Now look at the center right here. The center is c equals 4. Technically, you just let s minus 4 equals 0, and then you will have c equals 4 right here. I just replace s with c. Alright, so the center is c equals 4. You look at the interval right here. You put 4 in the middle, right? So this is negative 3, this is 3. This guy 4, it doesn't make sense, right? So you need to eliminate A and B, right? Only C and D, correct, right? Because you put 1 here, 7 right here, and 4 in the middle. Yes, makes sense, because the radius of convergence is 3. Now, next one, you need to check the endpoints, right? This one doesn't have endpoint. This guy has the endpoint right here, right? So you're gonna let s for 7, substitute 7 for s over here. So you're gonna end up with 7 subtract 4 is gonna be 3. So I have 3 to the end right here. Now 3 to the end and 3 to the end cancel out, right? So I have the series ends go from 0 to infinity of negative 1 right to the end times n plus 2 over n, right? Now we're going to take the limit of n plus 2 over n when n approaches infinity. Alright, so it's going to be limit of n over n when n approaches infinity, right? Because n much larger than 2, right? So it's actually 1, right? So this guy is different from 0, right? So by the n term test, this series diverges, right? So s equals 7 is excluded, right? Because we need the interval of convergence. The answer must be C. Now let's move on to question 2. Which of the following series are convergent? Alright. Now, number 1 right here. Look at the general terms right here. This guy actually the P series, right? Remember the P series. P greater than 1, the series converges. If P greater than 0 less than equal to 1, the series diverges. Right? Now P equals 2 greater than 1, so the series converges right here, right? So 1 is correct. Now number 2, look at the general terms right here. This guy actually harmonic series, right? Harmonic series, the series diverges because P equals 1 right here, right? So this one is wrong. Now number 3, this guy actually geometric series, right? Look at the first term and the second term right here, and the second term and the third term right here, right? You see that the common ratio is negative 1/3, right? You're gonna take the absolute value of the common ratio. It's gonna be absolute value of negative 1/3, and it's gonna be 1/3, which is less than 1. The series converges, right? So number 3 correct. So the answer must be 1 and 3, right? The answer must be C. Now let's move on to question 3. The Taylor series for a function f about s equals 0 converges to f for s between negative 1 and 1. The n-degree Taylor polynomial for f about s equals 0 is given by p sub n of s equals this guy. Of the following, which is the smallest number m, for which the alternating series error value guarantees this guy. Alright, so we need to rewrite the full Taylor series at s equals 1, right? So we have f of 1. Substitute 1 for s over here, right? So we have So this guy actually the alternating series, right? With the terms a sub k equals 1 over k squared plus k plus 1, right? Let's generate this one when k starts from 1 to infinity, right? So if k equals 1, we have 1 over 3, right? K equals 2, we have 1 over 7, right? K equals 3, we have 1 over 13. K equals 4, we have 1 over 21. K equals 5, we have 1 over 31, etc. Right? Now observe that each of these terms right here are positive. Right? And then the terms is decreasing, right? And finally, when you take the limit of this one, when k approaches infinity, it's going to be 0, right? So we can use the alternating series error bound, right? So it's going to be absolute value of r sub n always less than or equal to the next omitted terms, which is a sub n plus 1, right? We have the error bound is right here, right? So this guy less than or equal to m. M is the next omitted terms, which is a sub 5, right? Look at 4 right here. So a sub 5 is 1, 2, 3, 4, 5. The answer is 1 over 31. The answer must be C. Now let's move on to question 4. Which of the following statements about the series is true? Alright. So we're gonna let the whole thing right here be a sub n, right? So this guy actually alternating series. We need to find the limit of 1 over 1 plus square root of n when n approaches infinity, right? It's actually 0. Second one, don't worry about this guy, right? If n equals 1, you have 1 over 1 plus square root of 1 is going to be 2. N equals 2 is going to be plus 1 over 1 plus square root of 2. N equals 3, 1 over 1 plus square root of 3. The series has decreasing terms, right? Every single time it's going down, right? Because the denominator greater than the numerator. By the alternating series test, the series a sub n converges. Now, you need to determine if this guy converges absolutely or conditionally. The series of absolute value of a sub n becomes 1 over 1 plus square root of n. Remember, the whole thing right here is a sub n, right? So when you take absolute value, this guy right here gone, right? So you only have this guy. Now I'm going to use the limit comparison test. I need to find the limit of a sub n over b sub n when n approaches infinity. Now I'm going to compare this guy with 1 over square root of n, right? So I'm going to have limit of a sub n over b sub n. When n approaches infinity, it's going to be same thing as limit when n approaches infinity of 1 over 1 plus square root of n times square root of n over 1, right? So it's going to be limit when n approaches infinity of square root of n over 1 plus square root of n. Now when n approaches infinity, this guy much larger than 1, right? So it turns out to be limit of square root of n over square root of n when n approaches infinity equals 1, which is greater than 0, right? Look at this one, greater than 0. Now, if the bottom diverges, then the top diverges, right? So, I'm going to look at this guy right here, the bottom, which is this guy right here, right? But the bottom right here is divergent by the p series, right? You have the series 1 over square root of n is the same thing as series 1 over n power of 1 half, right? P equals 1 over 2 less than 1. The series diverges by the P series, right? This one diverges. Now, originally, you have this one converges by alternating series test, which is the whole thing right here. Now, we're going to look at this one right here, absolute and conditional convergence. This guy right here. If absolute value of a sub n diverges, which is this guy right here, right? But the series a sub n converges. This guy converges right here, right? Then the series a sub n is said to converge conditionally, right? So the answer must be B. Now let's move on to question 5. Which of the following series can be used with the limit comparison test to determine whether the series converges or diverges? Alright, so when you use the limit comparison test, you're going to check the quotient of the leading terms on the numerator and denominator. Numerator is right here, denominator is right here. So n divided by n cubed is going to be 1 over n squared, which is right here. The answer must be B. Now question 6. Which of the following series are conditionally convergent? Alright, so remember conditionally convergent means the series right here, I name this one as a sub n, right? This guy as a sub n, and this guy as a sub n. The series conditionally convergent if this guy converges, but the absolute value of a sub n diverges. Now we're going to check to see if the first one right here converges, right? So we're going to use the alternating series test, right? They are alternating series test, right? So we're going to find the limit of ignore this guy. It's going to be 1 over n to the 4. When n approaches infinity, it's going to be 0, right? And we're going to populate the series, right? So if n equals 1, we have 1 over 1, right? N equals 2, we have 1 over 2 power 4, right? N equals 3, we have 1 over 3 power 4, right? And observe that the terms are decreasing. By the alternating series test, this series converges, right? Now we do exactly the same thing for number 2 and number 3. They all converge by the alternating series test, right? Now we need to check the absolute value of this guy, right? So absolute value of this guy turns out to be 1 over n to the 4, right? Now we need to prove if this one is convergent or divergent, right? So of course this one is the P series where P equals 4 greater than 1, right? The series converges. So number 1, convergent. Now number 2, the series becomes 1 over n power 2 over 3, right? So this guy actually the P series, right? Where P equals 2 over 3 less than 1, right? The series diverges. Number 3, the series becomes 1 over n, right? This guy actually the harmonic series, right? And harmonic series diverges, right? This guy diverges, right? Satisfy this, right? So the answer must be C. Now question 7. Which of the following series is absolutely convergent? So we're going to review this one when the series is absolutely convergent. If the absolute value of a sub n converges, then the series a sub n also converges, right? Now we're gonna let this guy right here as a sub n, right? And if we take absolute value of a sub n, it becomes 1 over 2 n, right? Similarly, this guy becomes 1 over n of 1/2, right? This guy becomes n over n plus 1, and this guy becomes 1/2 to the n. Now this guy can be written as 1/2 the series 1 over n, right? So this guy actually the p series where p equals 1, right? P equals 1. So this guy actually harmonic series, right? So it could be divergent. Now the second one right here, p equals 1/2, right? Less than 1. So the series diverges. So we need to eliminate a and b, right? Because we need the series a sub n and the series of absolute value of a sub n converges. Now for c right here, we need to find limit of n over n plus 1 when n approaches infinity. It's going to be limit of n over n when n approaches infinity, and it's actually 1, right? Different from 0. So by the end term test, the series diverges, right? So we need to eliminate this one, right? This one converges by the geometric series test, right? Where common ratio is 1/2 less than 1, right? And original one is right here, converges by the alternating series test, right? I'm gonna leave this one for you to check. So the answer must be D. Question 8. Which of the following series converge? Now, number 1, this guy actually diverges by the n-term test, right? Because when you take the limit of n over n plus 2, when n approaches infinity, it's actually limit of n over n. When n approaches infinity, n equals 1, right? Not equal to 0. So by the n-term test, this series diverges. We substitute 1 for n. We're going to have cosine pi over 1, right? Substitute 2 for n. We have cosine 2 pi over 2, right? Substitute 3 for n. It's going to be cosine 3 pi over n, right? And if we simplify, it's actually cosine pi equals -1, so it could be -1 over 1. Cosine 2 pi equals 1, so it could be 1 over 2. Cosine 3 pi is going to be -1, so it could be -1 over 3. Right? Remember, cosine of odd pi is going to be -1. Cosine of even pi is going to be 1, right? So this guy actually alternating series. This series right here is the same thing as -1 raised to the n over n, right? So we're gonna find the limit of 1 over n when n approaches infinity. It's gonna be 0, right? And you look at the terms right here. Take absolute value of each terms right here, and you see that the absolute value of each terms is decreasing, right? So by the alternating series test, this series converges, right? And the last one right here, this guy actually harmonic series where p equals 1, right? This guy diverges, so the answer is B. Question 9. If the limit of this guy is finite, then which of the following must be true? So this guy actually the integral test, right? So we need to eliminate C, D, and E, right? Because this guy matches this and this only, right? Now, since the limit of this one is finite, it tells us that this series converges, right? So the answer must be A. Question 10. What is the value of the series 2 to the n plus 1 over 3 to the n? Alright, so we rewrite this one as 2 over 3 altogether raised to the n times 2, right? So the first term is when n equals 1, right? So n equals 1, substitute over here, we have a sub 1 equals 2 times 2 over 3. It's going to be 4 over 3, right? And the common ratio is 2 over 3, right? Since 2 over 3 less than 1, right? So this guy actually the geometric series, and it's gonna be converges to s sub infinitive equals a1 over 1 minus r, and it's gonna be 4 over 3 over 1 minus 2 over 3. So it's gonna be 4 over 3 over 1 over 3. Multiply the top bottom by 3. So the answer must be 4. The answer is C. Question 11. What are all values of P for which the infinite series converges? Alright. So we need to use the direct comparison test. Alright. Now we're going to take the leading terms on the numerator and denominator and divide them, right? So it's actually n over n to the p. So it could be 1 over n to the p minus 1, right? So we're going to compare this guy right here with this guy right here. Now observe that this guy is a sub n, this guy is b sub n, and a sub n less than or equal to b sub n, therefore greater than 0, right? So if series b sub n converges, then series a sub n must be convergent, right? In order for this guy to be convergent, and this guy actually the p series, right? P minus 1 must be greater than 1, right? So P greater than 2, right? So the answer must be E. Now let's move on to question 12. Which of the following series diverges? Number 1. Observe that sine s always less than or equal to 1, greater than or equal to -1, right? And pi right here actually 3.14, etc., right? So then sine 2 divided by pi always less than 1, right? And this guy actually geometric series, right? Where the common ratio is sine 2 over pi less than 1, right? And then the series converges by geometric series test, right? This guy actually the series 1 over n raised to the 1/3. Now this guy actually the p series, right? Where p equals 1 over 3 less than 1, right? Then the series diverges by the p series test. Now number 3, we're going to take the limit of e to the n over e to the n plus 1 when n approaches infinity. It's actually limit of e to the n over e to the n when n approaches infinity by relative growth rate, right? So this guy cancel out, the answer is 1, which is not equal to 0, right? So by the n term test, this series diverges. So the answer must be 2 and 3, which is D. Now question 13. Consider the series e to the n over n factorial. If the ratio test is applied to the series, which of the following inequality result implying that the series converges, right? So we're going to use the ratio test. So basically, the ratio test say limit of a sub n plus 1 over a sub n when n approaches infinity is actually limit of e to the n plus 1 over n plus 1 altogether factorial divided by a sub n, which is multiplied by its reciprocal, right? So it could be n factorial over e to the n. Now we're going to simplify this guy cancel out. We have e on the top, right? The bottom right here, you have n plus 1. Now when n approaches infinity, this guy approaches 0, right? Which is less than 1, right? So the answer must be D. Now let's move on to question 14. Which of the following series converges? For all real numbers s, right? Which means s could be anything, right? So now we're gonna test s equals 1 to see what happens. So this guy becomes the series 1 over n, and this guy diverges by harmonic series test, right? So answer choice A is wrong. Now this guy turns out to be the series 1 over n squared. This guy actually p series, right? Where p equals 2 greater than 1. So this guy converges. C is going to be 1 over n power 1 half, right? And this guy actually p series where p equals 1 half less than 1 diverges, right? So this guy wrong. Remember, B could be right, could be wrong, because we just check s equal 1. It say all real numbers s, so be careful. Now we're gonna let s equals e to check B. So the series B becomes e to the n over n squared. Now we're gonna find the limit of e to the n over n squared when n approaches infinity. The top is exponential function. The bottom is quadratic function. Exponential function grows much faster than quadratic function. So when n approaches infinity, this guy approaches infinity, which is not equal to 0, right? So the series diverges by n term test, right? We need converges, so this one is wrong. Now we're gonna test D using the ratio test, right? So we have limit of a sub n plus 1, which is e to the n plus 1 times s to the n plus 1 over n plus 1 factorial divided by a sub n, which is n factorial over e to the n s to the n when n approaches infinity. Now we're going to simplify this one, so to be limit when n approaches infinity of this guy cancel out, so we have e, right? This guy cancel out, we have s right here, right? This guy cancel out, so we have. Now since n approaches infinity, s not related, so we put s in the front, right? So it can be absolute value of s limit of e over n plus 1 when n approaches infinity. Right, so the bottom much larger than the top, right? So this guy actually absolute value of s times 0 is going to be 0, which is less than 1. So by ratio test, this series converges, right? For all real number s, right? Because s times 0 is going to be 0, the answer must be D. Now let's move on to question 15. What are all values of s for which the series converges? Observe that this guy actually geometric series, right? Where the common ratio is 2 over s squared plus 1, right? So in order for this series to be convergent, we need absolute value of this one should be less than 1, right? Now observe that the one inside the absolute value side right here always positive, right? So I just remove the absolute value side, right? So it's gonna be 2 over s squared plus 1 less than 1, right? Take reciprocal both sides, so it could be s squared plus 1 divided by 2 greater than 1, right? Multiply both sides by 2, so it could be s squared plus 1 greater than 2. Subtract 1 both sides, so s squared greater than 1, right? So then s greater than 1 or s less than negative 1, right? So the answer must be D. Question 16. For what values of P will both series converge? Alright, so the first one right here actually the P series, right? Where P equals 2P, right? So in order for this series to be convergent, we need 2p right here greater than 1, right? So p greater than 1 half, right? Now, this guy actually geometric series, right? Where the common ratio is p over 2, right? So in order for this series to be convergent, we need p over 2 less than 1, right? So then p less than 2. We combine this guy and this guy, it should be from 1 half to 2. The answer must be C. Now, let's move on to question 17. For s greater than or equal to 1, the continuous function cheese is decreasing and positive. A portion of the graph of cheese is shown above. For n greater than or equal to 1, the n terms of the series a sub n is defined by this guy. If the integral from 1 to infinity of g of s ds converges to 8, which of the following could be true? Alright, so this guy actually the integral test, right? So remember we have the formula. So when this guy converges to 8, then the series right here must be convergent to a number that bigger than this guy, right? So which is greater than 8. The answer must be C because we have 10 right here. Now let's move on to question 18. The power series b sub n s plus 2 to the n converges conditionally at s equals 1. Which of the following statement about the convergence of the series at s equals -6 is true? Alright, so observe that the series center at s equals -2, right? And the series converges at s equals 1, right? So we just draw the number line right here. Alright, the center is -2 and the series converges at s equals 1. So 1 is the endpoint. Radius of convergence is 1 minus -2, which is 3, right? So this is the radius of convergence. We're gonna count 3 units to the left from the center, right? So it could be -3, -4, and -5 right here. The interval of convergence is -5 to 1 right here, right? Now we look at this one right here, s equal -6 is outside of the interval of convergence, which is going to be divergent, right? So the answer must be B. Now question 19. The Markov series for the function f is given by fs equals this guy. What is the value of f of 3? So we have f of 3 equals the sum n goes from 0 to infinity of -3 over 4 raised to the n. And this guy actually geometric series where common ratio is -3 over 4, right? And absolute value of common ratio is equals 3 over 4, which is less than 1, right? Then the series converges to s sub infinity equals a sub 1 over 1 minus common ratio. The first term is when n equals 0, right? It's actually 1 over 1 minus common ratio, which is -3 over 4. So it could be plus 3 over 4, right? So it could be 1 over 7 over 4, and it could be 4 over 7. The answer must be C. Question 20. If the series a sub n converges and a sub n positive for all n, which of the following must be true? So if you have 0 less than b sub n less than equal to a sub n, right? Now if the bigger converges, then the smaller converges. The bigger right here a sub n, then this one b sub n. If the smaller diverges, then the bigger diverges. Now we look at this one right here, a sub n right here converges, right? A sub n greater than this one. So if this one converges, this one must be convergent, right? So we look for the answer right here. Which one smaller than a sub n? Actually this guy right here. Because we divide the series a sub n by a positive number, so it could be less than this one, right? So the answer must be E. Because a sub n converges, the smaller one converges by direct comparison test right here. Question 21. The infinite series a sub k has n partial sum a sub n equals n over 1 minus 4 times n for n greater than or equal to 1. What is the sum of the infinite series? So remember, the sum of an infinite series is the limit of its partial sums when n approaches infinity, right? So we need to find the limit of s sub n when n approaches infinity equals limit of n over 1 minus 4 n when n approaches infinity, right? So when n approaches infinity, this guy grows faster than 1, right? So it can be limit of n over negative 4 times n when n approaches infinity, right? So we can cancel out this one. The answer is negative 1 over 4, right? So the answer must be C. Now let's move on to question 22. Find the sum of the series right here. Alright, so observe that the power right here are even, right? The factorial right here also even. Think about the Taylor series of cosine, right? So remember, cosine s equals 1 minus s squared over 2 factorial plus s to the 4 over 4 factorial minus s to the 6 over 6 factorial plus s to the 8 over 8 factorial minus s to the 10 over 10 factorial, etc. Right? Let s equals pi, so we get this guy right here, right? So we have cosine of pi equals 1 minus, substitute pi for s, so we have pi squared over 2 factorial plus pi to the 4 over 4 factorial minus pi to the 6 over 6 factorial plus pi to the 8 over 8 factorial minus etc. Right? So the right hand side right here actually what we need to calculate right here, right? So we need to calculate cosine of pi actually negative 1, right? So the whole thing right here actually negative 1, right? The answer must be A. Now let's move on to question 23. Give a value of p such that this series converges, but this series diverges. Alright, so we're gonna start with this guy. This guy actually the p series, right? So in order for the p series diverges, this guy right here, 2p must be less than equal to 1, or p less than equal to 1 half, right? Now this one is the alternating series, right? So we're going to use the alternating series test to determine the value of p so that the series converges, right? So observe that p must be greater than 0 so that the limit of 1 over n to the p when n approaches infinity equals 0, and the series 1 over n raised to the p decreasing, right? So by alternating series test, the series converges, right? So we're gonna combine this guy and this guy. The answer must be p greater than 0, less than equal to 1 half, right? So here's how you show your work on the AP exam. Now let's move on to question D. Give a value of p such that this series diverges, this series converges. Alright, so observe that this guy is the p series. This guy also a p series, right? So the p series converges when 2p greater than 1, right? Then p greater than 1 half, right? The series diverges when p less than equal to 1, right? We're gonna combine these two guys. So 1 half less than p less than equal to 1. This one is the final answer. Now let's move on to question 24. The function f is defined by a power series for all real numbers s for which the series converges. Question A. Determine the interval of convergence of the power series for the function f. Now we're going to use the ratio test. The series converges when limit of this guy less than 1. Diverges when limit of this guy greater than 1. So keep that in mind. Alright, so we have limit of this guy right here. We're gonna let this guy right here be a sub n, right? So we have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity equals limit absolute value of a sub n plus 1, which means s minus 2 raised to the n plus 1 over 3 raised to the n plus 1 times n plus 2, right? Divide by a sub n, which means you're going to multiply by its reciprocal, right? So it could be 3 raised to the n times n plus 1 over s minus 2 raised to the n. Limit when n approaches infinity. Now this guy cancel out. We have s minus 2 left on the top, right? This guy cancel out. We have 3 on the bottom, right? Now we have n plus 1 on the top, left, right, and n plus 2 on the bottom. Now s minus 2 is not related to this one. I'm going to bring this one outside. Don't forget absolute value sign. Limit of n plus 1 over 3 times n plus 2, right? So it's going to be absolute value of s minus 2. When n approaches infinity, this guy right here approaches 1/3, right? So I put 1/3 right here, right? Now, in order for this series to be convergent, we need this guy less than 1, right? Now, I'm going to multiply both sides by 3, so it could be absolute value of s minus 2 less than 3, right? So it's going to be negative 3 less than s minus 2 less than 3, right? And then I'm going to add 2 3 sides, so it's going to be negative 1 less than s less than 5. Now, don't forget to check the endpoints, negative 1 and 5. Now, s equals negative 1. We substitute negative 1 for s into this guy right here, right? So, we have, and it's going to be the series n go from 1 to infinity. Negative 3 raised to the n can be written as 3 raised to the n times negative 1 raised to the n over 3 raised to the n times n plus 1, right? This guy and this guy cancel out, so it could be the series n go from 1 to infinity of negative 1 raised to the n over n plus 1. And this guy actually the alternating harmonic series, which is convergent conditionally. Now I'm going to check s equals 5, right? So the series becomes n goes from 1 to infinity. Substitute 5 for s, so it could be 5 minus 2, it could be 3. 3 raised to the n over 3 raised to the n times n plus 1, right? Now I'm going to simplify this guy and this guy, so it turns out to be, now I can rewrite this one as the series n start from 0 to infinity, right? And this guy becomes 1 over n, right? And this guy actually harmonic series, right? Harmonic series diverges, right? So the final answer should be this inequality right here. And you need to include s equal negative 1, right? Because this one converges, right? So the final answer must be negative 1 less than or equal to s less than 5. Question C. Use the first 3 non-zero terms of the power series for the function f to approximate f of 1. Use the alternating series error bound to show that this approximation differs from f of 1 by less than 1 over 100. The first 3 terms are right here. I'm going to copy them down. So you have f of 1. Substitute 1 for s over here. So if you simplify this one, it's actually 47 over 54. Now, next one, we need to use the alternating series error bound to show that this approximation differs from f of 1 by less than 1 over 100. You know that the power series for the function f evaluated at s equal 1 is an alternating series whose terms decreasing in absolute value to 0. The alternating series at about is the absolute value of the 4 term, right? Because this one is the 3 non-zero terms. So absolute value of f of 1 minus 47 over 54 less than the value of the 4 terms, which is, but s equals 1 right here, right? So I can remove s right here. I'm going to put 1 there. 1 over 108. And this guy actually less than 1 over 100, right? Now let's move on to question 25. The function g has derivatives for all orders. And the Maclaurin series for the function g is given by the alternating series. Using the ratio test, determine the interval of convergence of the Maclaurin series for the function g. So this question is similar to the question 24, right? So we have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity equals limit when n approaches infinity absolute value of negative 1 raised to the n plus 1 times s raised to the 2 parentheses, be careful, n plus 1 right here, and then plus 1 outside, over 2 parentheses, n plus 1 plus 3 outside. And then divide by a sub n, which means multiply by its reciprocal, right? So it could be 2n plus 3 over negative 1 raised to the n times s raised to the 2n plus 1. I'm going to simplify this guy. It's actually limit when n approaches infinity. Negative 1 raised to the n and negative 1 raised to the n right here cancel out. And you have negative 1 left. When you check absolute value, it's going to be positive, right? So this guy right here completely gone, right? Now the top right here becomes absolute value of s. Distribute this one, it could be s raised to the 2n plus 3, right? Times 2n plus 3 over. This guy actually 2n plus 5, right? Times this guy s raised to the 2n plus 1, right? Now this guy actually s raised to the 2n plus 1 times s squared, right? So this guy and this guy cancel out, right? So we have limit when n approaches infinity, right? Of absolute value of s squared times 2n plus 3 over 2n plus 5, right? So when n approaches infinity, this guy right here approaches 1, right? So we only have s squared left, right? In order for this guy to be convergent, this guy must be less than 1 by the ratio test, right? So it turns out to be negative 1 less than s less than 1. You're not gonna stop right here, right? Be careful. You need to check the endpoints. So you need to check s equals negative 1 and s equals 1, right? S equals negative 1, right? Substitute negative 1 for s into this series. So we have the series n start from 0 to infinity of negative 1 raised to the n. Negative 1 raised to the 2n plus 1 is still negative 1 because this is odd power, right? Over 2n plus 3. So this guy turns out to be the series n start from 0 to infinity. Negative 1 raised to the n and negative 1, it becomes negative 1 raised to the n plus 1, right? Times 1 over 2n plus 3, right? This one is the alternating series, right? So we need to use the alternating series test to determine if this one is convergent, right? So we're gonna let a sub n be 1 over 2n plus 3, right? Now we need to find the limit of a sub n. When n approaches infinity, it's gonna be limit of 1 over 2n plus 3 when n approaches infinity and is actually 0, right? The sequence a sub n right here is decreasing because when n getting bigger, a sub n getting smaller, right? So from these two guys, we can conclude that the series converges by the alternating series test. Now for s equals 1, we do exactly the same thing, right? So the series becomes -1 raised to the n times 1 over 2n plus 3, right? And you're going to do exactly the same thing as you did on the top, right? I'm going to leave this one for you to practice, right? So you can conclude that the series converges by alternating series test, right? So finally, you have s equals 1 and s equals -1 combined with this guy. So the answer should be -1 less than equal to s less than equal to 1. Now let's move on to question B. The Maclaurin series for G evaluated at s equals 1/2 is an alternating series whose terms decrease in absolute value to 0. The approximation for G of 1/2 using the first two non-zero terms of this series is 17 over 120. Show that this approximation differs from G of 1 over 2 by less than 1 over 200. Alright, this question very simple, right? Easier than the question 24C, right? So you have absolute value of G of 1 over 2. Subtract 17 over 120 should be less than the third term, right? Because this one is first two non-zero term. So the third term is right here, right? S to the fifth over 7. But s equals 1/2, right? So I have 1 over 2 to the fifth over 7, right? So it can be 1 over 32 over 7, right? It turns out to be 1 over 224, which is less than 1 over 200, right? And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand in mine.